Okay, I will start. We will talk about a Scala DSL for building secure and composable LLM prompts. We are developers at HiveMind Technologies. How many Scala developers are in the room? Oh, a lot of them. So the talk will be for Scala developers, but we will make it accessible for everyone. So we'll try to make it simple. So Izzy is going to tell about HiveMind.
Yeah, so we're basically doing data projects and cloud migration projects and all different kinds of branches, small companies, larger companies, and yeah, about 30 people that are working at HiveMind, and yeah, that's mostly about us. And we have a location in Germany and UK. That's basically it. And a bit of a disclaimer about the library. So we have built this explicitly for the talk. So we have been preparing it, and also don't dare to use it in production yet. It's not for that purpose yet. And yeah, it's all open source. So please have a look at the references later on, and then please feel free to maybe drop in some ideas or whatever.
Well, the first thing is we'll cover is why prompt safety matters. We will see some inspiration and ideas that we took from other frameworks or languages. Then we will see some examples, and then we will walk through the library, the basics, and then summary and future work.
Yeah, mind you, there's a small symbol for the examples.
Yeah, the puzzle there is, for example, this puzzle. Well, why prompt safety matters? Because security is a major concern in generative AI. Everybody is doing generative AI. Most companies have invested heavily on it. Most companies have technology developing on it, and nobody's taking security very seriously. So we want to avoid prompt injection, for example. That is when we want to discard previous instructions from the prompt. We want to also enforce prompt structure. We will validate these prompts some way, so we can send a prompt to an LLM that is mostly validated and safe too. Well, this is the first, well, we will see some design ideas that we will discuss in the beginning. First, we use the prompt builder pattern, the builder pattern. So we have a prompt builder, and we will do assignments for each of the fields, for example, the role and the task, and some other fields like example. We will be building a case class with all the fields, but this end up being too rigid, and composition is difficult. And also, if you look at the code is not very visible there, but you cannot see the whole text of the prompt in the same place. So it's difficult to know if the prompt is correctly built, or also can lead to ambiguities. For example, if you put a task, what should I put there in this field? You are a task, for example, you are as an assistant or just assistant. It leads to ambiguities. So although it's very easy to implement in Scala with case classes and copy message from case class to another, we discarded this option later on. So we took some inspiration and ideas from the Duby fragments, from Duby framework. I don't know if you use Duby. Scala has this feature of interpolators. If you use S and a string, then it's like it's like the printf from C, that you can pass arguments to this string, and the arguments will be passed to this interpolator and will be composed as string. So in Duby, this FR interpolator is built to build fragments of SQL queries. If you do things like this, FS select name from employees, then you create a fragment object, and then you can later compose and execute the queries. For example, you can pass a parameter, and then you can combine these two by concatenation, and then we'll get the full query. Yeah, then you can execute the full query. And for the next slide, this is when, for example, when you have a fragment that has a parameter, the code, for example, where code equals code, then we will pass is like a placeholder that we can pass some information to this fragment, to this interpolator. So we will use the same idea in our interpolators, our prompt interpolator, to pass different parameters to the prompt. Yeah, you can go on. This is you.
So a few design ideas, as we heard maybe in other talks already. It's a good idea to separate execution from the actual values. And so that's what's also one of the ideas behind it. So the trade of the prompt was a bit the starting point for that. And different cases like maybe the empty object, a new line, or the literal case, which is just capturing some text, and maybe a margin character if you want to do some strip margins, like you maybe have to indent the sequence at the beginning, or capture a value. It's encoder and validator. And basically then in the end we have to also construct more complex scenarios, and that's where the combine primitive comes in. That was one of the main ideas at the beginning. And then capture a left prompt and a right prompt in order to construct the whole tree of prompt segments. Then if all of this comes together, then you can create maybe something like a extension function on the prompt type that allows you then to render this whole thing, which deconstructs the given elements and then goes through them primitive by primitive and turns everything into a string in the end in order to be able to consumable the LLM. And here we, for instance, are also building the strip margin implementation. So we wrap that character and do just pass on the strip margin onto the strings strip margin implementation here. Then the new line, which is a simple new line, empty, it's just the empty string. And for the value, we take its encoder, encode the value. And for the combination, we take the left, render it, and we take the right and render it. That's basically a recursive call. And for the value itself, we now ignore the validation at this stage, but we have captured it. And this instantly also gives a bit of the question, where and how should the validation actually happen? And do we capture the validator in the early phase, or do we capture it later? So that was a bit of a question at the design phase that also kept going through the whole stage of designing the library. And then on to...
Yeah, so we will comment now what we want to achieve with the library. What were the ideas at the beginning, and the most we want to define prompts, visual and in an intuitive way, using a prompt interpolator with multi-line strings, and we should be able to pass arguments to these prompts. We should validate prompt parts or the whole prompt using a side-effectful computation. And also we want to be able to tell the library we want structured outputs. For example, I want a response in this JSON format. For example, the prompt interpolation should behave this way. We should put prompt and a string, could be a static string, and we could have different parameters, for example, an int or a string, 43, my name is, and then we will use this prompt interpolator to pass the int and the string, and it should render this is an int, then the value, and so on. We should be able also to combine prompts, for example, saying a role, you're a helpful assistant, then a task, you're giving a list of words, and then we should be able to use a combiner operator like this, role, new line, task, or we could use the interpolator to paste the values or the prompts inside the prompts. For example, nested prompts like this is similar to the previous line. Should be. Then also we want to use this multi-line string, so we can check the whole text of the prompt in this way. So it's very easy to insert values or parts of the prompt in a multi-line string, and we should be able to use the strip margin as a Scala standard way.
And when it comes to validation, we've introduced now a basic validator for taking a prompt and validating it to an IO of a Boolean. So here we can basically add anything for validating it. Could be extended prompt injection, protection, kind of logic that you want to do. And once that's presented as a given, it is available for us for later. And then you take a prompt, and that's now, if you jump back one, where is it?
Up. Let me here.
Yeah, exactly. So if you have, for instance, now a prompt which contains a not so nice message that you're asking the LLM to help you build a bomb, so that could be something that you want to prevent, of course. And now when it comes to evaluating it, it will now be picked up either explicitly when you pass it on using, or you can also just use it once and use it everywhere with the given instance that you have provided before. And one of the main extension points now is the template, which basically is something like a function that takes an A and produces a prompt later, where you can then encode whatever you want. It's the main extension point. For example, if you have a user-defined type, like a person object that has a name and an age, and you provide this now a template for it that encodes those values in a version that you want them to be appearing in your prompts. And once you have specified this, then you can use it basically in your prompts directly. So in the next, we see now here's a person called Alex, 34 of age, and then you can directly just use Alex in the prompt there, and it will print as expected. So it says this is a person Alex, 34 years old, and that's it.
If, for example, for the structure output feature that we want, for example, if you have a case class sentiment analysis with a word and the sentiment, if it is positive, neutral, or negative, then if you instruct the library to use this JSON schema, you can pass the case class in a static way, and the type to this applied method on the JSON schema, and then you will get something like this. Please return response on the following JSON format, and something like this will be printed, indicating the format of the response that we expect. And this is all the attempts we did and discussions. We were working like 3 months on this library, and we played a little bit with the covariance, invariance, and so on, and lazy validation, or having a lot of tests until we get to the unifier interpolator. That was the final version. So the basics, and now I will explain on the basis of the library. We have a case class prompt that is just a string wrapper. So every time we say prompt, you can think of a string. We have primitives for new line and empty. It's just an empty string or a new line character. Eventually, everything becomes a prompt. Prompts can be nested. And this acts as a base primitive for the DSL. Prompt, as it is just something similar to a string, is just a monoid. We can define monoid in cats to have free functionality, like the plus operator or the combine all. Defining the empty string as the empty prompt as the empty string, and the combine as the string concatenation, like this. If we have to combine a left and a right prompt, then we just concatenate the text and create a new prompt from it. These are some examples on the free functionality that we get from cats. If we have 2 prompts, then we can combine with this plus with the bars from cats. And in the other example, for example, we can intercalate a new line between a list of prompts, or we can just play with some optional values. For example, if you have some prompt 1, none, prompt 2, and so on, we can get the concatenation of every one of all the prompts using cat's functionality, like the combinator. Yes. Also, we get the map n for tuples and combine all for a list of prompts. For example, tuple map n, we will apply this, for example, this tuple from 6 and from 7, and we will get some 6, 7, for example, the concatenation. The other The combine all example is the same. We have a list of options, and we can combine all, combine all on the list, and we will get the concatenation of all the prompts.
Well, and the other primitive is the template. So as already introduced earlier, it's mostly capturing the notion of a function from A to prompt. And it's implemented as a type class in this case. And it's acting as the main extension point. It's not a prompt yet, but it will eventually become a prompt at some point. And earlier stages, we also had a bit of an idea of call it encoder, but because it's capturing more the concept of turning things into many different shapes and having not just one particularly encoding for a type, we chose the template as the name for it. The way it's constructed, it has one argument, and that makes it contravariant because it's appearing in contravariant position. And that gives us a lot of freedom also in terms of composition. So when we build the contravariant monoidal feature from cats for this type, we get a lot of composition features on top of the templates. So that requires us to provide a contramap function. Notice, I don't know, is anyone familiar with contramap or not? Not? Yeah, it's basically like map. The only thing that changes is that the order of the f is turning in the opposite direction. So instead of providing an f of a, and the function from A to B, we have now a function from B to A, and that returns a template of B in this case. And that also gives us the opportunity to provide a product function, which then now takes just two templates, A and B, FA and FB, turn order, then create a template of the tuple of the two. So it's just taking the monoidal combine, takes the two values, applies them, and we get the combined result there. Here we have an example for it. So John, in this case, should now be integrated into one template, and that can be now used to create more larger prompts. And here we have its name and its age being put into place, and then this template has been defined as a given, can be then automatically used. Now we take another prompt like the system prompt, you're a helpful assistant. It's just a static prompt, and we combine the two now, and we have the system prompt at the beginning, and then later we just name John here, and it will automatically find the template description for it, and we'll use that to then generate the result. Then we come to more advanced features. We've talked about the monoidal combine, and we decided to also extend it a bit to be not only type homogeneous, and on the other side, the contravariant composition features that we get from the template, but to combine the two and go for something that is a bit more heterogeneous so that we can combine things a bit more freely. So at the bottom, we see a prompt and a prompt, which now results into a prompt. If we go and combine a prompt with a template, the resulting type is going to construct a new template where the prompt of the left part is going to be merged into the template that was already there, and you get back a template. And there's plenty of more options that you can do to combine this. Maybe you can shout in what you might think, what the others are. So for the prompt and the prompt, we already just saw. So that's going to be a prompt in the end. If we have the template on the left and the prompt on the right, then the template wins. And the symmetrical case, of course, for the other side. And now a bit more interesting cases, we also have some flattening semantics built into this combiner. So if you take a scalar value on the left and a tuple on the right, maybe have a guess what this could result in. Sorry?
A triple.
Yes, exactly. It's going to be a triple. So it's just going to take the A and prepend it here. Or here it's going to be appending it. And the last section is going to then concatenate the two. That's going to be semantics of the plus combiner.
So the combiner definition in this slide is going to be an extension method from any type L to with any type on the right R, and we will use a combiner implicit definition like in this using statement, and we will use the apply method from this combiner from the left and right part like this. This is the applied definition from the combiner trait, and we will have the left part as a type, the right part as a type, and the output type as a result of this applied method. So, for example, we will define in the combiner companion object, we will define different givens definitions. So we have like a resolution for each kind of combination we want to do. For example, if you have a prompt on the left and a prompt on the right, we just use the simple monad combine that we have before, and left combine right. If we have a prompt on the left and a template on the right, we will return a template on the right. So what we do is to create the prompt on the right side and then combine with the left prompt. This is the symmetric definition from the previous one. If you have a template on the left and a right the prompt on the right, and if we have, for example, both scalars and both sides, we have two templates, and then in here we use the monoidal product that we defined before to combine these two templates. In the following is for combining tuples. If we have tuples on the left and tuples on the right, we will use this helper method tuple combination, and this split the implicit definition that we will use to split the output that we want to get. We will split in the left part and the right part, and then we will use the monoid combine to combine the two prompts. For example, if you have a value on the left that is an int, a string, or whatever, and a tuple on the right, then we will use. Can you show the? Well, we use the tuple combination that we saw before to get the template of L prepended to the tuple R. The other one is symmetric but appending instead of prepending. And if we have both tuples, a tuple on the left and a tuple on the right, then we will use the same tuple combination helper method, but the resulting type will be the concatenation of the left tuple and the right tuple.
Yeah, so now that we have seen a few combinators, we want to put them all together, and the main interaction point is going to be the prompt interpolator, and it's acting as the unification of all of the combinators that we have seen into one. So it's basically like the Swiss Army knife in this library that is going to produce either simple prompt values or combine them in any direction as you want. And the interpolator implementation has to do quite some type wrangling in order to get the job done, and we introduced a few steps. It captures the static parts, which are the literals, from the prompt interpolator, and it captures all the dynamic parts as the arguments, which in this case is an arbitrary type, and it can also be an empty tuple. It's a bit cut off there on the edge. But it's just the end of the line is empty tuple. So we either get an empty tuple when the prompt interpolation value doesn't contain any values that the user have provided as variables or something like that. And when they are provided, then it will just put them in either as a singular value or as a tuple. Then when we have them, we're going to transform them in separate steps. So we have a reducer, a sequencer, and a transformer in the end. There's also the margin stripper that went into the library version that we have right now here at this stage as an implicit or given instance. And then it ultimately results into the transformed shape that we want to have in the end, which we saw from the table earlier. And what it's doing, it's just taking the static parts, it's going to map over them, it's modifying them with a strip margin being applied, but we call it from the inputs. And then it's just going through a sequence of calls of methods. These are polymorphic functions. So we're just going to call the reducers, apply. The result is going to directly being sent over to the sequences inputs, and that result is going to be then the input for the transformer, and that's going to be the ultimate result. And basically we have this very linear flow of transformations. So we start maybe with a mix of inputs given as values A0s up to ANs, mixed with some templates, B0 or of B0 and template of BN or whatever. And also we expect that the values that we provide, all the A's have a matching given instance of a template attached to them. And when that's in place, we can all reduce the A's and mix them from the left to the rightmost template, in this case, to its neighbor. And then we result in the first step without any concrete values. So those are all reduced in the first step. And then we end up with something being always a tuple. Either it's going to be empty when there were no values and no templates, or it's going to be the resulting templates that we found. And in the next step, we are going to sequence that. So we have a tuple of templates and we turn it into a template of a tuple. And the result thing is going to be just taking out this weird, synthetic thing that just has been constructed, which is the template of an empty tuple, which doesn't make sense at all. It's just an intermediate thing that has been then reduced at the very final step and turns that into a prompt. And at the bottom you see the resemblance of that.
Sure.
No problem.
Okay.
So that's what you see in code, basically. So you would have the A's in there and the templates in there, and those can also be referenced and constructed here if you want to say, oh, I want to use a template here directly.
Good. Now we will talk about how can we validate these prompts. The question that we have raised before, who should validate these values that we get into a prompt? In the end, we decided to validate the final prompt string. So everything we will send to the LLM, we'll validate it before, and not validate all the values. These A's won't be validated in a separate way, because it could be valid in one context and invalid in other contexts. So we have this prompt, this validate trait that is a function from prompt to a side effect computation IO of Boolean. In this case, we use CATS IO, but it could be any kind of effect system. And in this IO, we can do anything. For example, check a black list of words. We can go to a database, or we can call a second LLM as a judge to say, hey, this prompt is safe to send to the LLM, and the judge will say yes or no, depending on the content. We will use an extension method on the prompt type, so we can call validate on any prompt and use the validator that is in scope in the givens definition. This is the extension method, and the apply will be the function to call for validation. Validate is also a monoid, so if you define the empty validate as a true, and we combine the left part and the right part with an and then we will get a monoid. So we can combine the validations in different ways. For example, in the next slide, if we have, for example, a validation function that checks the word bomb. If we pass you are a bomb assistant, then this validation should be false because it detects this word. And if you have, for example, a composition using the AND logic, if we check for the contains, if the prompt contains the word hello, and in other validation we check the word in the word. If we combine these two validations using the monoid combine, then we can check different prompts. For example, the first one is valid because it contains both words, and the second is invalid because it contains only hello word. Yeah, this is the assertion from the tests. So the first one is valid and the second is invalid.
Yeah, and then there are some small extensions that we also ship with it already. Like what we see oftentimes in prompts is that you want to have separation between separate sections in your prompts. So there's a notion of a section already built into the library. So that's a type that we ship then. And you can just specify a title and a value that you want to be in that section. And now there seems to be two different camps in how you want to write those sections. Some use XML notation and others use a different one, but this is how you would encode them, and that's what we already provide. So you have the title being put in the tag, open and closing tags, and the value in the middle. Doesn't do anything besides that, and you can then just import the necessary section formatting option you like or need, or your LLM is more responsive to, and maybe pick another one for another, like the all caps notation, which is the second, which just takes the title, makes it all caps, followed by a colon, and then your value. So here it's in use. So you have maybe a system prompt again, very simple. Then you define maybe two sections, one for the input parts of your prompts and the other one that you want as an expected output for describing maybe a section of examples. And then this can be then explicitly stated that you want to use now the margin stripper, which we saw earlier now as an import for the pipe operator. That's the usual strip margin character in Scala. And now also explicitly stating that you want XML as the formatting option. And then you can basically write this down and you're done. So just have some imports and that's it.
Well, as a summary, we could check that some of the new Scala 3 features were very advanced. We didn't know before, so we discovered some nice features built in the library. So we use tag classes a lot, interpolators, and given declarations very heavily. The whole library is like 300 lines, so it's very compact. The design and the build is an elegant library that is easy to use, is simple, and it's composable, easy for the user. And the complexity behind all these combinators is hidden by the library, is inside the library. So for the user will be easy. Library is built on top of CATs, providing a lot of free functionality, as we mentioned. The final prompts should be validated. The final string prompts will be validated. Validation can run any kind of side effect of computations, as we discussed.
Well, ideas for future work would be to extend for other effect systems, make it more agnostic in that sense, then also introduce a bit more of LLM samples to have it locally running, of course, and provide also some blocks for the DSL sections and headings, roles, and tasks that main competitors like OpenAI already provide, where you can say, okay, I have a role and maybe other features that other LLMs provide, and just give a bit more of already batteries included, so you don't have to specify those primitive extensions your own. The strip margin functionality turned out now as a implicit, which is a bit of a weird situation for, let's say, Scala users, which are used to just call strip margin on a string. So the result now being a prompt or a template makes that a bit of a difficult choice. Could reintroduce the value in between stage where we first capture the structure of the prompt and all its components, and then later lazily evaluate its value again. That took a few turns and routes to get to where we are now. So that gave us maximum composition features and, let's say, also nice ergonomics from the compiler. And we were jumping a bit up and down. But yeah, we could bring that back to some reason. And I think the most important thing would be the prompt injection protection part, to have a big eye on it. So we take these values that go into these prompts and validate them separately. That's mostly what library users are already doing with their values before they go into prompts. So there's no real value of adding an additional validation layer unless you want to say, oh, this value is not valid in a prompt or this prompt. You probably also want to make sure that the result that comes out is always going to be valid. So it's not always going to be making sure that the values that go into it being validated separately and the sum being separately validated on its own, making sense. So the word bomb can happen to be in any usual sentence, but the whole structure around is going to determine whether it's going to be a prompt that you want to avoid sent over to your LLM or not. So the result in the end is always going to be required to be looked at. That's why we chose then to maybe push it into this very abstract form. And yeah, that's basically it.
Well, some announcements for my wife Alejandra was support at home for the Lambda Worlds organizers for selecting this topic for presentation. Hyphen directors, Franz Unai for allowing us to work on this library. To Isaias for all the long debates and discussions for the library. Some reference if you want to download the code and see how it's built. Some articles there on security and LLMs and cause effect and Doobie, shapeless. So you can check the slides afterwards. Some questions?